Hello my friends and welcome back to the You Can Do TV channel.
The Ichthys LNG project gas export pipeline represents a major engineering and construction milestone, with Saturn awarded responsibility for the design, engineering, and installation of the offshore and nearshore pipeline systems. The project includes the short approach works in Darwin, installation within Darwin Harbor, offshore pipeline laying, and preparatory activities in the subsea field. The project scope also involves managing regulatory and environmental requirements specific to Australia, ensuring compliance throughout all phases of pipeline installation. Saturn deployed the Castor 1 vessel for the project, marking its first operations in Australia, its first shallow water pipeline installation, and the first installation of a concrete-coated subsea pipeline for the company. Engineering and project planning were conducted in the first office phase, with specialized teams focusing on critical works inside Darwin Harbor. Preparatory work included establishing the short approach, securing the path line, and protecting the pipeline corridor to meet both environmental and operational standards. A major technical achievement of the project was the record-setting pipe laying operation by Castor 1, completing 122 triple joints in a single day, equivalent to over 4.5 kilometers. The vessel began operations in 60 meters of water and progressed to complete the subsea line at the Innsfield in 250 meters of water depth, demonstrating advanced subsea capabilities, precise navigation, and high operational efficiency. Logistics and project coordination played a critical role, encompassing crew movements, material handling, and project resource management. The project required meticulous planning to ensure timely delivery of pipes, equipment, and personnel, effectively creating a mobile, operational town to support continuous offshore construction activities. The high technology on board, combined with skilled personnel, allowed for precise control of welding, concrete coating, and pipeline alignment to meet stringent HSE and engineering standards. The Ichthys LNG pipeline project highlights Saturn's growing expertise in subsea pipeline installation. With this project, the company has successfully installed one of the world's longest subsea pipelines, solidifying its competence in complex subsea operations. The experience gained in shallow and deepwater installations, concrete-coated pipelines, and high-output offshore operations reinforces Saturn's capability to deliver safe, efficient, and technically demanding pipeline projects globally. The pipeline construction process begins with clearing and grading the easement to create a stable, level surface for safe and efficient installation. This step includes removing vegetation, debris, and obstacles, while ensuring proper drainage and alignment along the planned route. Following this, pipe sections are delivered to the site for stringing and bending. Stringing involves laying out the pipeline along the easement in preparation for welding, while bending adjusts the pipe to match changes in alignment or terrain. Welding of pipe sections is carried out next, using precise techniques to ensure strong, leak-free joints. Each weld undergoes non-destructive testing, such as X-ray or ultrasonic inspections, to detect potential defects and verify structural integrity. Once tested, weld joints are coated with protective material to prevent corrosion and environmental damage. Finally, trenching is performed to place the pipeline below ground, followed by backfilling and compaction to restore the terrain and provide long-term support and stability for the pipeline. The Rockland Street Storm Sewer installation involved the precise placement of reinforced concrete pipes to manage stormwater flow and prevent urban flooding. The project began with a detailed survey of the site to identify existing utilities and establish proper pipe alignment and grade. Excavation was performed to the required depth, with trench walls stabilized using shoring where necessary. Bedding material was placed and compacted to provide uniform support for the pipe barrels. Pipe sections were carefully lowered, aligned, and joined according to manufacturer specifications, ensuring tight joints and proper slope for gravity flow. Backfilling was completed in controlled lifts, compacted to prevent settlement, and the trench was restored to roadway grade. Continuous inspection and quality control ensured the sewer system met design standards and long-term durability. The pipe installation process is a structured operation designed to ensure quality construction and proper alignment, slope, and support. Initial steps include inspecting all delivered pipe for cracks, dents, spalls, or compromised coatings, and verifying lifting equipment capacities. Excavation of the pipe trench follows, considering embankment requirements and maintaining a minimum of 12 inches of cover from the pipe crown to overlaying pavement. Trench width is calculated as the pipe outside diameter plus 4 feet, with proper slope for trenches deeper than 3.5 feet. Trench bottoms are proof-rolled and compacted using approved equipment, such as self-propelled trench rollers or hand-operated vibratory plates. Bedding material is then placed, 6 inches of number 8 aggregate for concrete pipes, and number 2 aggregate for metal or thermoplastic pipes. Pipes are positioned with bells or grooves, upgraded into hubs, and joints are sealed with caulking, gaskets, or bands according to material type, with geotextile wraps applied as required. Backfilling is done in 4 to 12-inch compacted lifts, ensuring lateral support, especially for thermoplastic and metal pipes. Compaction is verified visually or via nuclear density tests. Quality control documentation is completed on Form CS6, confirming compliance with alignment, slope, and compaction standards. Proper installation ensures structural integrity, drainage efficiency, and long-term performance. The Bridgewater Bridge project in Tasmania is a major infrastructure initiative featuring a 1.3-kilometer span across the River Derwent. VSL and Boogie's construction are using a match-cast precast method, optimizing parallel construction of piers and superstructure. With 20,000 cubic meters of concrete and 6,000 tons of rebar, it's a long-lasting, sustainable engineering feat.
During the N40 South Ring Road flyover scheme in Cork, Ireland, a critical lifting operation took place at the Sarsfield roundabout, involving the installation of 18 precast concrete beams. Traffic diversions were implemented to ensure safety while operations were conducted over live roads, allowing uninterrupted progress on the flyover construction. On Tuesday, the 9th of April 2013, work commenced on the west span at 8 p.m., scheduled over 2 night shifts to minimize disruption to daytime traffic. Each beam measured over 39 meters in length and weighed up to 105 tons, demanding precise coordination and lifting capability. To handle these massive loads, CHL deployed a 350-ton crane and a 500-ton crane, working in tandem to lift, position, and secure each beam onto its designated support points. The operation required meticulous planning, including site preparation, crane positioning, and verification of ground stability. Engineers ensured the safe placement of each beam, aligning them with millimeter-level precision to meet structural and safety standards. The two-crane system provided the necessary lifting power and redundancy to handle exceptionally heavy beams safely while maintaining balance and stability during lifts. With careful sequencing, the nighttime operation was executed efficiently, allowing all 18 beams to be installed without incident. This project demonstrates the integration of high-capacity cranes, strategic traffic management, and expert engineering coordination to accomplish complex urban flyover construction, ensuring safety, precision, and minimal disruption to the surrounding community. When engineers and builders embarked on the construction of the 1915 Canakkale Bridge, they were not just connecting two shores, they were pushing the limits of modern bridge engineering. Spanning the Dardanelles Strait in Turkey, this suspension bridge boasts a record-breaking main span of 2,023 meters, making it the longest in the world. Every aspect of its construction demanded advanced planning, precise engineering, and careful coordination among hundreds of specialists. Construction formally began in March 2017, led by a consortium of Turkish and South Korean firms. The total bridge length, including approach viaducts, reaches 608 meters, carrying a 6-lane motorway that links Europe and Asia. The first stage involved deep foundation work. Massive caissons were placed into the seabed, some reaching 45 meters below sea level, providing stability for the enormous loads of the bridge. On these foundations, engineers erected 2 steel towers, each standing 318 meters tall, forming the tallest points of the structure and requiring meticulous alignment for both aesthetics and structural integrity. The towers were built from prefabricated steel blocks, some weighing up to 800 tons each. Modular construction allowed these massive sections to be lifted into place using specially designed tower cranes, improving both worker safety and assembly precision. In total, the towers incorporated over 42,000 tons of steel, assembled with millimeter-level tolerances. Once the towers were in place, attention shifted to the bridge deck and suspension system. The deck is a twin-box steel girder, designed to resist high winds, seismic activity, and maritime vibrations. Measuring 45.06 meters wide, it accommodates 3 motorway lanes in each direction, along with maintenance walkways. The deck sections were prefabricated and floated into place, then lifted and connected using advanced rigging techniques, reducing on-site construction time and exposure to the elements. Suspension was achieved using 2 massive main cables, each consisting of thousands of parallel steel wire strands. These cables, with diameters approaching 876 to 888 millimeters, were spun and compacted on site. To protect against corrosion, dehumidification systems were installed inside the cable sleeves, ensuring long-term durability in the harsh marine environment. The project demanded advanced logistics and coordination. At peak construction, over 5,000 workers were engaged, supported by more than 740 pieces of construction equipment. Teams managed marine foundation work, steel fabrication, cable spinning, deck erection, and continuous quality control. Seismic analysis, wind tunnel testing, and robotic alignment tools were essential to guarantee the bridge's performance under dynamic loads. Prefabrication, modular assembly, and precise engineering allowed the project to proceed efficiently. After the final deck block was installed on the 13th of November 2021, engineers conducted comprehensive inspections to confirm alignment, load distribution, and structural integrity. The bridge officially opened on the 18th of March 2022, dramatically reducing travel time across the Dardanelles and connecting two continents. The 1915 Çanakkale Bridge is more than an infrastructure project. It is a testament to modern engineering, combining steel, concrete, advanced fabrication, and innovative design. Its record-breaking span, towering steel pylons, and massive deck illustrate what is possible when precision, planning, and human ingenuity converge, establishing a new benchmark for suspension bridges worldwide. From foundation to final deck installation, the bridge embodies decades of civil engineering expertise, international collaboration, and a commitment to quality that ensures it will serve for generations to come, linking Europe and Asia with unprecedented efficiency and elegance. A site inspection was conducted on the Ston Bridge as part of the broader road connectivity project with southern Dalmatia. Engineers and project managers reviewed ongoing construction activities, assessing structural progress, safety compliance, and quality of materials used. Key focus areas included the integrity of bridge supports, alignment of deck sections, and installation of guardrails. Observations were documented to ensure adherence to design specifications and project timelines. The inspection also facilitated coordination between contractors and local authorities, optimizing workflow and addressing potential challenges. This visit reinforced commitment to delivering a safe, durable, and efficient transport link across the Ston corridor. The Liebherr LTM 11200-9 is a flagship mobile crane in the industry, representing the pinnacle of heavy lifting capability in a single transportable unit. Designed for extreme lifting tasks, the crane combines advanced hydraulics, robust structural engineering, and cutting-edge control systems to handle some of the heaviest loads encountered in construction, energy, and industrial projects. At the heart of the LTM 11200-9 is its 9-axle all-terrain chassis, providing exceptional mobility and stability across challenging terrains. This configuration allows the crane to distribute weight efficiently, reducing ground pressure while enabling travel at highway speeds between job sites. Each axle is equipped with independent suspension and steering, providing maneuverability in confined urban environments or on uneven industrial grounds. The crane features a 100-meter main telescopic boom, extendable with high-strength steel sections to reach substantial heights while maintaining minimal deflection. For maximum versatility, the LTM 11200-9 can be equipped with a pendant or lattice jib, extending the reach up to 188 meters, ideal for heavy lifting at power plants, shipyards, or offshore platforms. High-performance hydraulic cylinders and load-sensing systems provide precise control during lifting operations, allowing operators to handle massive components safely and efficiently. Liebherr's varioballast system further enhances performance by adjusting counterweight placement and optimizing crane stability dynamically during complex lifts. Advanced computer-aided control systems monitor load moments, boom angles, and ground conditions in real time, ensuring safety and compliance with operational limits. The crane's versatility is matched by its transport efficiency. Despite its massive lifting capacity, the LTM 11200-9 can be broken down into manageable sections, allowing transport over public roads with standard permits. Assembly and setup are streamlined by modular components, quick connect systems, and detailed engineering documentation, minimizing on-site preparation time. From heavy industrial installations to wind turbine erection, the Liebherr LTM 11200-9 demonstrates how engineering excellence, hydraulic innovation, and structural precision converge in a mobile crane, delivering unparalleled lifting performance while maintaining mobility, safety, and operational flexibility across demanding construction environments. At the 2015 Liebherr Customer Days in Ehingen, a breathtaking demonstration showcased the precision and power of Liebherr's crawler crane lineup. In perfect synchronization, 7 massive crawler cranes performed a choreographed display of lifting and balance, highlighting both engineering excellence and operator skill. The lineup featured the colossal LR 11350, 2 powerful LR 1600 halves, 2 agile LTR 1220, and a compact LTR 1060. This live performance underscored Liebherr's technological leadership in the heavy lift sector, captivating audiences with a rare fusion of brute strength, hydraulic precision, and structural harmony in motion. As the cranes swung into motion, lifting and counterbalancing each other using massive ballast weights and suspended loads, spectators witnessed an extraordinary feat of coordination and machine stability. Each crane demonstrated its unique strengths, from high lifting capacities to exceptional mobility on tracked carriers. The RK5000.010 bucket chain excavator, a colossal machine weighing 5,600 tons, is shown here departing the CSA lignite strip mine in Komarany, Urbanus, Czech Republic, on its final journey to a designated parking site above the mine after operations ceased in early 2017. Built in the former CSSR in 1983, this giant underwent 3 general overhauls up to 2016, maintaining its formidable performance over decades of service. Measuring 160 meters in length and 40 meters in height, it featured a powerful hydraulic movement system circulating 15,000 liters of oil and required a team of 6 operators. The RK5000 could extract up to 4,450 cubic meters of overburden per hour with a peak power draw of 9,000 kilowatts, making it one of the largest and most capable excavators of its class. In the dynamic heart of the port, an extraordinary logistical challenge unfolds as Ferrovial undertakes the transport of the Komatsu 4800 XPC shovel to Minera Escondida. The operation begins within a hive of coordinated activity, where teams prepare to move one of the largest and most advanced mining shovels ever engineered. More than a machine, the 4800 XPC represents cutting-edge innovation, with every component designed for maximum output, structural integrity, and long-term durability in one of the world's toughest mining environments. Each oversized module of the shovel, massive, precision-built, and weighing hundreds of tons, is carefully lifted and secured onto specialized heavy-haul transporters. These multi-axle platforms, equipped to handle extraordinary loads, form a slow-moving convoy that advances methodically through port facilities and public roadways. The maneuvering resembles a finely tuned choreography where every turn, incline, and obstacle is managed with millimetric accuracy by Ferrovial's experienced crews. The convoy transitions from the bustling port environment toward the remote desert, where stark landscapes replace city noise. Across each kilometer, the transport operation highlights the synergy of brute mechanical power and precise human expertise. More than a simple relocation, this journey symbolizes technological progress and the operational commitment behind modern mining. As the 4800 XPC nears its destination, where it will soon become a central workhorse of Minera Escondida, it carries the promise of enhanced productivity, efficiency, and a new chapter of innovation for one of the world's most significant mining operations. The Saturn's SGC-120 represents one of the most advanced heavy-lift solutions in the world, designed for extreme lifting tasks in construction, energy, and industrial projects. As a self-erecting giant crane, it combines immense lifting capacity with mobility and precision, making it ideal for handling ultra-heavy components such as refinery modules, offshore platforms, and large-scale infrastructure elements. At the heart of the SGC-120 is its modular design, allowing rapid assembly and disassembly on-site. The crane can be configured in multiple ways depending on project requirements, including variations in counterweights, boom lengths, and lifting radius. With a maximum capacity of 200 metric tons, the SGC-120 can lift loads that few other cranes in the world can handle, and its boom can extend up to 120 meters. The crane is equipped with hydraulic and electronic control systems that provide real-time feedback on load weight, boom angle, and wind conditions. These systems ensure safe operation, even under challenging environmental conditions. Advanced stabilization mechanisms, including adjustable outriggers and counterweight optimization, allow the crane to perform lifts with maximum efficiency while maintaining full compliance with safety standards. Transportability is another key feature. Despite its enormous lifting capacity, the SGC-120 is modularly transported, enabling deployment to remote or constrained project sites. Each module is designed for road transport and assembled on-site using specialized rigging equipment and heavy lift assistance. Operators benefit from a state-of-the-art cabin control system, providing precise handling and visibility for complex lifts. Whether positioning wind turbine components, petrochemical modules, or large bridge sections, The SGC 120 delivers unmatched lifting performance with exceptional accuracy. The Saturn's SGC 120 is not just a crane. It is a mobile engineering solution that integrates mechanical, hydraulic, and electronic systems to achieve feats of lifting that redefine what is possible in modern construction and heavy industry. Its combination of raw power, precision, and versatility makes it a preferred choice for projects where traditional cranes would be insufficient. At Chevron's Richmond refinery, the replacement of the fluidized catalytic cracker marks one of the most complex maintenance undertakings in modern refinery engineering. The FCC is central to gasoline production, using a blend of thermal energy, mechanical systems, and chemical reactions. Operating under intense heat, low pressure, and continuous catalyst circulation, the unit endures extreme tensile stress, thermal cycling, and erosive forces, conditions that demand periodic large-scale refurbishment to maintain efficiency and safety. In preparation for this maintenance window, massive new FCC components were transported from fabrication facilities across the United States. These pieces include the new reactor head, regenerator head, and cyclone assemblies, each engineered to withstand the severe reactions inside the FCC. On site, crews begin by lifting the new reactor head into position above the cyclone system, a delicate operation requiring millimeter-level precision. Nearby, teams assemble the new regenerator head and its cyclone cluster, creating a structure that will soon replace the decades-old unit. To handle the extraordinary weights involved, the refinery brought in one of the world's largest mobile crawler cranes, delivered on 160 trailer trucks and erected specifically for this project. Its lifting capacity makes it capable of removing and installing components exceeding several hundred tons. Once the crane is fully rigged and tested, the operation transitions to heavy lift mode. Technicians unbolt and detach the old regenerator head and its cyclones, a lift that demands strict coordination between rigging crews, crane operators, and structural engineers. After a controlled 4-hour descent, the old assembly settles into a ground-level cradle beside the new replacement unit. Next comes installation. The crane hoists the new reactor head and cyclone system, a combined assembly weighing more than 750,000 pounds, and guides it into its final position atop the FCC. Precision alignment ensures that sealing surfaces, catalyst pathways, and mechanical joints interface correctly. Inside the regenerator, a newly fabricated combustor cone is lifted into place. This cone plays a critical role in restoring catalyst activity by ensuring uniform combustion and heat distribution. Technicians then maneuver the regenerator's cyclones around the cone, locking each unit into its engineered orientation. The entire operation combines heavy lift engineering, refinery process expertise, and meticulous planning, an industrial ballet completed under tight schedules to return the FCC to service and keep fuel flowing to millions of drivers. On January 7th, at approximately 12:10 a.m., A 640,000-pound petrochemical splitter was transported along White Mud Drive at the 50th Street intersection in Edmonton, Alberta. The massive unit is destined for the Heartland Petrochemical Complex, currently under construction near Fort Saskatchewan. This splitter is a critical component in the facility's production process, designed to separate propylene from propane. Once separated, the propylene undergoes further processing to produce polypropylene, a versatile and recyclable plastic widely used in packaging, automotive parts, and consumer goods. The transportation of such an oversized load requires precise planning, including route surveys, coordination with local authorities, and specialized heavy-haul equipment. Escorts and safety measures ensured minimal disruption to traffic while protecting both the cargo and public. The successful delivery of this splitter highlights the engineering, logistical planning, and operational expertise necessary to move ultra-heavy industrial components safely to large-scale petrochemical facilities.
The manufacturing sequence of a Cochrane boiler starts with numerically controlled plasma cutting to profile flat steel plates with high accuracy. These plates are then hydraulically rolled to form cylindrical shells, followed by submerged arc welding of longitudinal seams, ensuring strong, continuous welds. Quality control measures are enforced rigorously by both Cochrane's in-house inspection team and an independent inspectorate. Critical welds are verified using X-ray technology for internal integrity. Tube plates are precision machined using CNC vertical milling machines to ensure accurate tube hole alignment. Manual welding, performed by certified professionals, is applied to key structural joints. All pressure-retaining welds undergo non-destructive testing. A bowling hoop-style furnace barrel is then welded to the combustion chamber, forming the internal firebox assembly. This, along with the front tube plate, is integrated into the boiler shell. Smoke tubes and stay tubes are installed between the tube plates, either expanded and welded. After tubing, the entire boiler shell is pressure tested hydraulically and inspected externally. The Cochrane boiler adopts a robust 3-pass configuration. First pass through the furnace, with the second and third passes through banks of small-bore smoke tubes. Constructed to British Standard BS 2790, it is designed for oil, gas, or dual-fuel operation. Access doors allow internal inspection and cleaning. Water level is monitored via gauges, and a safety valve protects against overpressure. Feed water pumps supply the boiler, with optional TDS control systems and blowdown valves managing water quality. All electricals are pre-wired to a side-mounted control panel, completing the package.
Channel. Mezzo Peru's technical service process starts with detailed data collection using SCADA, vibration analysis, oil testing, and 3D laser scanning to detect wear and deviations in crushers, sag mills, and thickeners. This data feeds into CAD-FEA and DM simulations for process optimization. Overhaul and repair plans are developed with precise scheduling, utilizing the 100-ton crane capacity at the Rio Seco facility and polymer ceramic megaliner production at Ate Lima. Components undergo robotic welding, stress relief heat treatment, and CNC machining with tight tolerances. Assembly includes laser alignment, sensor calibration, and rigorous testing under no load and 110% load conditions. Post-testing, equipment connects to Mezzo's IIoT platform for real-time monitoring and AI-driven predictive maintenance. This integrated approach extends overhaul cycles, reduces energy use by up to 12%, and ensures high safety and reliability standards.
The Hankook propulsion shaft lathe is a precision machine tool designed for the fabrication, machining, and finishing of large-diameter marine propulsion shafts used in ships and industrial applications. This lathe is engineered to accommodate shafts of considerable length and weight, providing stable support throughout the machining process. It features a robust bed and rigid headstock to minimize vibrations, ensuring high-precision turning operations. The lathe is equipped with adjustable tailstocks and steady rests to support long shafts during rotation, reducing deflection and maintaining concentricity. The spindle is driven by a high-torque motor capable of handling heavy cutting loads, while the carriage and cross-slide mechanisms allow for precise longitudinal and radial movements. Advanced control systems enable accurate feed rates and cutting depths, ensuring uniform material removal along the shaft's length. The Hankook lathe supports multiple operations, including turning, facing, tapering, and grooving, and can machine keyways, shoulders, and fillets required for propulsion components. Its tooling system accommodates a range of cutting inserts and attachments for specialized operations. Safety features include emergency stops, protective shields, and interlocks to prevent accidents during heavy-duty machining. The lathe also incorporates lubrication and cooling systems to extend tool life and prevent overheating of both the workpiece and cutting tools. Through its combination of rigidity, precision, and operational flexibility, the Hankook propulsion shaft lathe ensures that high-performance shafts meet stringent dimensional tolerances and surface finish requirements, critical for optimal propulsion efficiency and long-term reliability in marine environments. A traditional concrete spun pole production line in China begins with the fabrication of the steel reinforcement cage, a critical step that defines the internal structural strength of the concrete pole. This task is performed by a dedicated steel cage welding machine, which automatically winds and welds longitudinal and spiral steel wires into a precise cylindrical frame. The machine ensures uniform pitch, correct cage diameter, and adequate overlap at reinforcement joints, which are essential for resisting tensile forces once the pole is under service load. After completion, the finished steel cage is transferred to the mold assembly area. Here, a two-part steel mold is opened and cleaned, then coated with release oil to prevent concrete adhesion. The steel cage is carefully inserted and centrally aligned within the mold, using spacers to ensure uniform concrete cover during casting. Next, high-performance concrete is prepared in a central batching station. The mix typically includes cement, crushed stone, fine sand, water, and chemical additives to improve workability and durability. Once ready, the concrete is poured into the mold around the steel cage using a vibrating feeder depending on the facility's level of automation. The closed mold is then clamped securely and transferred to the centrifugal spinning station. This spinning machine accelerates the mold to high rotational speeds, typically 700 to 1000 RPM. The centrifugal force compacts the concrete against the mold walls, eliminates voids, and forms a dense, high-strength outer shell around the steel cage. Excess water and air are expelled during spinning, enhancing the concrete's final strength. Here, controlled temperature and humidity accelerate cement hydration, allowing the concrete to achieve its initial set within 8 to 12 hours. Once curing is complete, the mold is opened, and the hardened concrete pole is extracted using hydraulic demolding equipment. The finished poles are transferred to a storage yard for natural curing, which typically lasts 7 to 14 days. During this period, the poles gain their full mechanical properties. Final inspections, labeling, and optional surface treatments, such as polishing or painting, are conducted before packing and transport. This step-by-step method, starting with the automated production of steel cages, ensures a structurally reliable concrete pole widely used in power distribution and communication networks throughout China.
In the race to expand solar energy, speed and safety are essential. That's where the RPD-35 from Built Robotics comes in, a robotic pile driver transforming solar farm construction. Mounted on an excavator, it carries up to 200 piles on board and drives them into the ground with GPS-guided, sub-centimeter accuracy. Automating this once labor-intensive task triples productivity, placing over 300 piles per day. With more than 18,000 autonomous hours and a perfect safety record, the RPD-35 reduces risks, boosts efficiency, and accelerates the solar revolution, helping us power the future, one precisely driven pile at a time. The FreeFalcon Mobile Fall Protection Anchor, a compliant EN 795-2012 Type E system, features a mobile mast with a pivoting arm and integrated safety module. With a 10 meters working radius, overhead anchorage prevents trip hazards, ensures 360 degrees mobility, and delivers reliable fall arrest while remaining easy to reposition on site. The FreeFalcon Mobile Fall Protection System is positioned on site using crane lifting eyes and maneuvered via a pallet truck for stable placement, even on uneven surfaces. Before operation, trained and certified personnel reset the fall indicator, close the hydraulic valve, pressurize the unit, and release the pin to enable 360 degrees arm movement. In the event of a fall, the arm locks immediately to reduce swing risk. The integrated rescue device then lowers the worker safely within 2 minutes, ensuring rapid, effective recovery. The FreeFalcon Mobile Fall Protection Anchor is an innovative system designed with over 30 years of industry experience to address risks where collective fall protection is not possible. Independently tested to EN 795-2012, Type E, ANSE Z359.18-2017, and ASNZS 5532, the FreeFalcon ensures safety and mobility. Upon a fall, its patented arm drops, stabilizing the base and locking in the fall direction to reduce swing hazards. Rescue is achieved within 2 minutes using the integrated descent package. Easily moved by a pilot truck, it provides overhead fall protection across all construction environments. In a rugged limestone quarry, Three eccentric crusher buckets, the XC20, XC30, and the latest XC50, operate side by side, showcasing their raw power and efficiency. Mounted on different excavators, these high-performance crushing attachments reduce massive limestone blocks into reusable aggregate directly on site. The XC20 tackles smaller material with speed and precision, ideal for mid-size carriers. The XC30, a step up in capacity, handles denser, larger chunks of stone effortlessly. Meanwhile, the new XC50 dominates with its reinforced frame and expanded jaw opening, built for the heaviest applications. All three units feature patented vibration technology, maximizing throughput while minimizing stress on the host machine. With minimal maintenance, low fuel consumption, and fast processing rates, eccentric crusher buckets are a game-changer in quarry operations. Together, these machines deliver a synchronized performance, transforming hard limestone into valuable product quickly and economically, right at the point of extraction. On train. At the vast coal mines operated by PT Asmin Kwalindo Tuhub, one of the world's largest hydraulic mining excavators comes into play, the mighty CAT 6090 FS, formerly known as the RH400. Towering and formidable, this giant machine is engineered for high-volume overburden and ore removal in open-pit mining environments. The CAT 6090 FS boasts an operating weight of approximately 1,000 tons and is typically paired with ultra-class mining dump trucks for efficient material handling. Its dual 16-cylinder diesel engines deliver over 4,500 horsepower combined, powering an advanced hydraulic system capable of filling its 52 cubic meter bucket in a single pass. This allows it to load a 400-ton haul truck in just a few cycles. Designed with productivity and durability in mind, the 6090 FS features rugged undercarriage components, a reinforced boom and stick structure, and an operator cabin equipped with state-of-the-art controls for enhanced safety and comfort. Every movement of this hydraulic behemoth is a display of raw mechanical power and precision. At sites like Tuhub, the CAT 6090 FS plays a crucial role in maintaining efficient output, moving massive quantities of earth and ore with unmatched consistency and force. On Kuris. On April 7, 2012, Newport News Shipbuilding erected the first 717 metric ton flight deck section on the USS Gerald R. Ford, CVN-78. Incorporating combat systems and electronic spaces, this milestone brought the carrier to 75% structural completion, marking a major step forward in assembling the next-generation nuclear-powered aircraft carrier.
Feet. VoxelJet's 3D printing technology enables the production of highly detailed plastic parts for investment casting. Using a powder-based process, components up to 1,000 millimeters long and 320 liters in volume can be manufactured without tooling. CAD models are printed layer by layer using PMMA powder and a binder, allowing for complex geometries with undercuts. After hardening, unprinted powder is removed, and the part is wax-dipped for smoothing. These printed models are processed like traditional wax patterns. Burnout leaves no residue, enabling clean casting with stainless steel at 1,600 degrees Celsius. The final parts undergo finishing, inspection, and testing, offering a fast, cost-effective alternative to conventional casting methods.